worked on last summer, which is focused on synthesis and characterization of silver nanoparticles, which are often called AgNPs, and that way I'm going to refer to them in my presentation. So most of the part of my project I based on the literature of these authors, which are Prishepa, Dawadi, and their corresponding collaborators. They both have articles that are from a general overview of current investigation techniques, properties, etc., and the synthesis of silver nanoparticles. So having said that, a nanoparticle is a particle of matter that is in between the range of 1 and 100 nanometers in diameter. Silver at a nanoscale exhibits unique chemical, biological, and physical properties. And the most relevant one, the one that has had most relevance in the last couple of years in the biomedical research, is the strong antimicrobial activity, which allows these silver nanoparticles to target bacteria in multiple ways. So, having a dive in the literature, the most relevant properties for myself are the physical, chemical, and biological ones. As being the physical ones, the base of them all, from my point of view. First of them is the high surface to volume ratio, which in simpler words means that the smaller a nanoparticle is, the higher surface area that it's going to have. By having a higher surface area, we're going to have more atoms displayed over that surface, and therefore we're gonna favor the ion release efficiency, which in fact gets done better when in an aqueous environment, which can be the cellular cytoplasm, the body fluid, etc. And these properties head up the base for the biological properties, which the most relevant, as I said, is the antimicrobial activity, which basically means that the silver ions cause bacterial membrane disruption and the generation of reactive oxygen species, which cause oxidative stress and damage lipids, proteins, DNA, etc. So what's the approach for this project? We wanted to compare current traditional synthesis methods in the synthesis of nanoparticles, especially silver nanoparticles, as we've read in the AgNPs and Alsbecky articles, that synthesis method matters as it influences in the particle size, stability, cost, and even in the environmental impact. So currently, the traditional synthesis methods are basically chemical methods using chemical reducents that can cause or have an outcome of toxic agents to the environment, whereas green science has offered some other green synthesis methods that can have a more eco-friendly outcome using plant extracts. So the methodology we used was based on the articles I said before, the overview of silver nanoparticles, and this one especially from Alsbecky and their collaborators that specifically use Coriandrum sativum, which was the plant that I used. So as for the methodology, we divided the synthesis routes in two routes, the chemical and green one. Where the green one, we subdivided it in a hot method and a cold one, which was done under room temperature. As for the three synthesis methods, we used silver nitrate as our silver precursor. And for the chemical method, we used as our reductor and stabilizer tannic acid solution. Whereas for the green methods, we used Coriandrum sativum extract. This is a plant extract. And the way that we could determine that the silver nanoparticle formation was done was by the color change. Whereas in the chemical method, we saw that this is the natural color of the tannic acid, which is a little yellow color. And by the formation of nanoparticles, we ended up with a more gray tone solution. Whereas for the green methods, we've got the green tone solution from the extract. and having as a result or as an outcome a yellow brownish tone for the solution. And the difference between these two, as I said, this was done with temperature as a catalyzer for the reaction, and for the cold one, we just did it at room temperature. This is some evidence from the chemical method synthesis. I don't know if you can really appreciate it, but here's the yellow original tone and the transformation to the gray tone that I just told you. And for the green method, this is the plant extract, and this was originally a video, but it shows up how the change color thing that I just told you happens. Further, the silver nanoparticle formation, we did some characterization to the samples, which was SEM, DLS, and EDX. So to start off with the results, we did the dynamic light scattering analysis. This is basically a study that tells us the particle size distribution of a sample. And as you may see, these are the graphs that we got as a result. The first one englobes the chemical method, the second one, the green hot method, and the third one, the green cold method. As we may see, both the three methods had an outcome of particles above the 100 nanometers. I know that you may not really appreciate the resolution, but this is 100 and this is 1,000. So our nanoparticles seem to be above the 100 nanometers, and that, as we saw the color changing thing, we can, according to literature, assure that there was a nanoparticle formation. But what we're seeing here right now is that we are having particles above the 100 nanometers. So we can suggest, or this result can suggest, that parander Cetivum did reduce effectively, but did not stabilize the nanoparticles. Given that these can be, this result can be given as the nanoparticles are starting to agglomerate and make clusters. We then made the cyanic electron microscopy. This is the chemical method nanoparticles, the green hot method, and the green cold method. By seeing these micrographs, we can indeed see that there was a formation of nanoparticles. As we can see in the hot green method, we can see a lot more dispersion and reaction rate. I mean, we can see much more nanoparticles here than in a cold method, but that's something we're going to discuss a little later. And for determining the nanoparticle size, we did a SEM micrograph analysis, and we determined approximately, for the chemical method, a diameter of 13 nanometers, around 12 nanometers for the hot method, and surrounding the 11 nanometers for the green cold method. So why are we seeing this discrepancy in our results from the past analysis and this one? We then further made a EDS analysis. This is an elemental diffraction X-ray spectroscopy that is done along or simultaneously with the electronic microscopy. And this basically tells us the elemental composition of the sample that we're looking at and that we're analyzing. So for the chemical method, we see, it doesn't have much resolution, but the elements, basically the elements we have here are the elements that we had as our silver precursor and the tannic acid elements. There's not much big of a deal right here. But the important thing, or what has been of relevance in this study, is the results in the green methods. Something that have in common, these two methods, no matter the difference in the temperature thing, is that they both contain chlorine in their composition. Multiple studies, and as this one's right here that I wrote below, Both of these authors made silver nanoparticles using plant extracts, and they both had the same situation of the presence of chlorine in their samples. They determined, or they have stated, and this is what I based my results in, that when chlorine is in presence of silver or vice versa, they tend to bind together. They go along well, so they tend to form silver chlorine, which reduces the available silver ions that, instead of nucleating, they bind in with chlorine. And this results of a mixture of AgNPs and silver chlorine, which promotes the clusters. Therefore, we can assume that this is a reason in which, if we didn't sonicate the nanoparticles just before the DLS study, this is why we got these results that were with nanoparticles or particles above the 100 nanometers. So as we are seeing as well, we've got much more elements here in the cold method rather than in the hot method. And this is because of the temperature effect that we also is also one of the things that we wanted to test. Given that, according to Przyczepa, an author that I mentioned before, he noted that temperature is a catalyzer for the reaction and favors nucleation, which is the formation of nanoparticles. So given that information and that statement, we can say that a hot method gets us a faster nucleation and better dispersion. Whereas with a cold method, we get slower nucleation, more silver chlorine, and larger clusters. And we can verify that in the micrographs that I showed you before. As you can see, in a hot method, we get much more reaction rate and dispersion of the nanoparticles. Whereas in a cold method, we're seeing that these tend to agglomerate. There are very, very little nanoparticles, which is one of the targets that we have, but they are tending to agglomerate, and this is because of the presence of the silver chlorine. But this is not necessarily bad, as in a cold method, we did not just only preserve this component, but other functional groups that can be phenolic groups, phenolic compounds, for example. And these other minerals within the silver chlorine can become a more biocompatible material and may enhance the antimicrobial activity. So as a conclusion, by comparing the chemical ingredient synthesis, we could see clear differences in the AgNPs, size, composition, dispersion, etc. As we have proven, apparently, that temperature and time in a green synthesis are key. As for a cold method, we preserve functional groups and potentially have more biocompatible materials. Whereas for a hot method, we've got faster nucleation and less silver chlorine formation. The key point of this investigation is that none of other methods can be better than other. It's just that according or depending of the application that we want to give it is the method of choice that we're going to have. Thank you.
¿La importancia o qué es lo que está haciendo?
Yo trabajo actualmente de ingeniero en procesos de manufactura en una empresa de equipo de equipo ortopédico que entra dentro de la rama médica. El inglés es, yo creo, sin importar si elegimos el área de investigación, de biomédica, de industria, en cualquiera, e incluso mientras somos académicos, en cualquiera de las áreas en las que nos encontremos, el inglés es súper fundamental y práctico. En industria toda la documentación es en inglés, en el hospital todos los manuales están en inglés, en investigación los artículos de mayor relevancia, las revistas son en inglés, y los artículos también con mayores citas que solemos pues citar nosotros en nuestros trabajos también son en inglés. E igual, como lo que menciona Eliseo, los libros todos han sido en inglés, los que hemos leído.
Gracias.